Hi everyone, welcome to our talk about 3D case. We are going to walk you through some of the recent work that has been done at CDX. And I'm David Ratchkov, and with us we have James Wong, again, continuing from the previous presentation. How many of you have not heard of CDX before? All right, welcome to Planet Earth. Let me first do a quick intro of CDX. CDX stands for Chiplet Data Exchange. It's a work stream under ODSA, Open Chiplet Economy. And our focus is on adopting or developing standards for exchanging data. Specifically for chiplets. So today we are going to walk you through some of the recent work that we have done. But before I get to that, let me first say a couple of words about why we are doing this. Right? The chiplet ecosystem is quite complex. There is a lot of different players that would participate in the definition of a chiplet system. We have the silicon foundries, we have designers, we have IP providers, we have chiplet providers, we have substrate fabs, and we have tests. And all of these different players would need to talk to be able to talk to each other, to exchange rules, to exchange parameters, to exchange data in general. And our intent is to have a common language for everybody to be able to speak, so that the exchange of data is kind of natural and easy. Our intent is to have less of PDF files being exchanged, where the PDF files may be of good quality, bad quality. Then we have the human factor in trying to convert rules. So because of that, what we are working on is something we call 3DK. 3DK is a common exchange format that would address the need of different players. We have several different pieces in that, and I'm going to walk you through each one and see how those get applied. And later on, James will give you some examples of the recent work that has been done. So in 3DK, right now we have identified 6 different pieces. Probably the easiest one to start with is actually the CDK, the chiplet design kit. We defined that a couple of years ago, and really, that defines a set of models that a chiplet vendor might need to provide to chiplet integrator, so that they are able to plug that chiplet into their system. Then we have the SAPI kit. The intent of that is to be able for a chiplet vendor, or actually IP vendor as well, to be able to provide data about the parameters of their IP. What are the jitter requirements? What would be the loop inductance requirement, so that a designer can take that and start integrating that IP and chiplet into their system. Then we have the assembly design kit. That is one critical piece in being able to put chiplets together. In the assembly kit would have rules about bump patterns, spacings, die-to-die spacing, die-to-edge spacing, and so on. And the idea is when you are planning your system and you want to put the chiplets together based on different vendors, you can create a floor plan that would actually work. Material design kit is also one of the critical pieces. Being able to exchange data about what materials are used and actually are available for your design is one critical piece of information. And we want to be able to exchange that data in a digital format. Not a PDF format where you have to go and find what the value is and plug it somewhere in the tool. The idea is to automate that process. There's many different materials and different parameters that go with that. So having a standard way to exchange that data is one of the things that has been identified as actually needed. Then, as Rajesh mentioned, we also we're looking at test, and that is basically a description about what the test pins on a given chiplet, what the test pins are, where they are, which are sacrificial paths. And one of the interesting things about the 3DK is it's meant to be a live format. Where you would start at the beginning of your flow with one set of 3DK data, and once you have your final product, you would have the different set of data, right? Because you have built the system, and now you can describe your system also in 3DK. So it's meant to be a format that gets updated throughout the design flow. And speaking of flow. The question is where and how do we apply these pieces? We are looking at 3 different areas, right? At the architecture phase, naturally, we have the biggest set. That's one of the things you would discover if you've not done it yet. The chiplets, at the very beginning, lots of work needs to happen. And all of these pieces of data about what materials are used, what my package stackup is, what my rules are, what the chiplets need in terms of bumping, how they place them, warpage, mechanical, things like that, right? All of that needs to happen at the very beginning, and that's where the majority of inputs would come in. As you go through the design process, you would look at tests, how things get connected, and you would also look at when routing the package, you would need a PDK. One thing that has been done in the silicon world with PDK is you don't have to think about the rules, right? You just get your PDK and you kind of run with it. In the packaging world, we're not there yet. We want to get there, where you would basically be able to just load one file, and that will have all your rules about spacing, stackups, materials, vias, all kinds of, all the different rules would be captured in that. And finally, at the very end, really, at the sign-off, we are going to use some of the 3DK pieces to actually do sign-off. And at the very end, once you have the chiplet system ready, you would actually hand off a 3DK to the next level. You would describe what the test pins are, what the power integrity needs are, and so on, right? It would be 3DK, but with different pieces of data. With that, I wanted to hand off to James to talk about a couple of the pieces that are near completion, and he will walk you through some of the examples and what's in that. James.
All right. Thank you, David. Yes, as David has mentioned, I think this is part of the overall, I think the ambitious goal we're trying to achieve is to cover end-to-end of silicon, I think, or 3D IC more specifically designed from end to end. I think all the information from beginning all the end required. I think today we all know is pieces of information everywhere. So the effort is trying to put everything in well-defined format and structures, and then and that structure can be share not only I think between people, human, but also to electronic or EDA tools and consume them. So so one area I think we started focusing on is the material design kits. I think this is talk about all the materials properties. I think very important. I think as you heard earlier, I think in the thermal, mechanical, even electricals like SIPI, I think that are required to know what materials contents of it. And then compatibility analysis, I think this is then I think thermal analysis, mechanical analysis, all the tools require these informations to consume and then to provide the right analysis informations. So yeah, overall, I think to ensure there is performance and then the material selection and then the design to provide the a more seamless design flow and manufacturing flow that we have today. So let's look at these some of the properties that we mentioned earlier. I think thermal, really focusing on thermal conductivities, and then with mechanical that address the strength, flexibility, durability, and then electrical, there's conductivity or insulation as well. So you can see the two examples on the right. I think they're somewhat typical, some more complex. I think related to the stress worsen the strength. I think then you have a different kind of material, you have different kind of graph. And then you have a thermal versus a temperature that they're changing over graph. How are you going to get this information? I typically see this in data sheet in some data form, in the PDF. We want to digitize them in some format. That's the XML that we are working on. Here's an example. I think actually adopting from the ML is one of the very comprehensive material spec. So this kind of high level, I think example that we have been using, I think to trying to measure a demo example in OCP that we're working on. I think we do have substrate and dielectric here. We can see there's material information about what kind of material type they are and what the CTE value, the Young modulus, and then for dielectric you have the different CTE and different Young modulus, and then the loss tangent, etc. And then that will be everything translated into the XML format and the structure you can see on the right-hand side, where I think that will be able to consume. I think to electronically. I think you get more accurate information and easier consume that way. And then that is one, I think, area we work on. And then another area is the ADK that we're working on. So you can see this is the assembly design case. Is in hierarchical. This is the structure we kind of adopting from the Intel, which is also part of the participant in the CAS group and OCP. I think it's overall. So here we can see there's a header, and then you have include other files you can add to it, and then you have a overall tolerance, and then of course you need a version to map in on that, and then the rest you have kind of multiple subsection. You have layers, and then every layer you have kind of defined different layer of the rules for that, geometries, paths, and then potential outline sections. We come to more example on this one. So as mentioned, I think hidden information include all the silicon technology. I think what kind of the micro using. I think what kind of the device family that you're targeting. Global tolerance, defined tolerance. I think just software we can introduce that in the hardware as well. I think where I think you can define global, and then you apply across the entire the spec. But then you can also have local kind of tolerance that. Different tolerance that needs for locally, and then you have version layers and geometry as mentioned. I think is the paths. So I think you have C4 paths that you use to define the types, dimension. Potential, I think again important used in a lot of this kind of testing tool and manufacturing tools that you need to know the rotation. There are many different types. I think the location they are and coordinate. So we want to incorporate that. I think cover all of them. The outline section, subsection, I think typically this will be important in the rules. When you do your placement, you need to know the clearance, how close they can be, on how far they should be, and then we also working on the active interpolers. So I think this is more specific, the rules related to active interpolers. So here's an example again. I think the demo. I think that we have been using. I think the from the OCP demo, this one we're using the glass kind of interposer. So they have 3 layers here. You can see there's kind of 4 micron on the thickness for example, and then you have different minimum the wires, I think, and then you have a VR, I think, between the 3D. So you can see, I think, this should be like cover, and we can able to map that in our structure. So that's kind of like the purpose of that. Yeah, and that's it. I think for the trees, the tools, I think kind of like ongoing. I think like the substrings, I think under CDS, where I think I focus on MTK and ATK today. We are having a bi-weekly meetings on every Thursdays. So it's kind of alternate week. I think 1 week will be on MTK, and then we will be on the ATK. That will happen at the 9 a.m. Pacific time. So we have like the GitHub repo. You can go and check it out. And then like we also working on the specification, which we targeting, I think, like sometime end of this year. And then there's a group IOs which you can subscribe. Please join us. I think we to have more participants. That's all from the presentation. Today we will open it up for questions.
So I have a question. You mentioned the test design kits. Can you give me any more information? I know Rajesh also mentioned it, because that's pretty interesting. Because chiplets, put them together. What kind of what data or what are people willing to share for the system?
So for the test design kit, we are not trying to capture what tests are run and how they are run and so on. What we are trying to capture is describe on the boundary of the chiplet what are the test pins and how they look. And when I say how they look specifically for sacrificial paths, being able to tell the flow that here's a path and it's actually sacrificial. And then we expect that the flows will take care of the rest of it, right? The interesting about sacrificial paths is you will design for it, you will do wafer tests with it, but when you ship your final product, it's not going to have the sacrificial path defined, right?
Exactly.
So that's what I mentioned. That's specifically what I had in mind when I was saying that the 3DK kit is something that will change through the flow, right? You would need to know where your sacrificial paths are for wafer tests, but you don't care about the functional bumps, the micro bumps, and things like that, right? Once you at the flow where you are shipping the final products, which is after final test, you need to carry only the micro bump locations and definition, and then drop the sacrificial paths. That's one of the aspects. The other one is to being able to describe which pins are actually test pins.
Right. Yeah,
right?
like the tap controller pins or.
That's right.
Yeah.
And that is important because what I learned from Rajesh also, we would define the connectivity between chiplets based on functionality, but then it also has to be correct from test connectivity point of view. Yeah. Right? We don't want to hook up clock to test clock to a test data pin, right? That's not going to work. So having that description is a first level sanity check. Okay. Make sure that we didn't do anything that's not going to work at all, right? Yeah. So that's the two pieces of that.
Okay, and that's work that's going to be started.
Yes.
In the near future.
Basically, it's an extension to CDXML. Yeah. In CDXML, we already have the pin definitions, where they are, what they are. Right. We are going to enhance CDXML with the geometrical information, and then a section in the test pins, a section for each pin that tells us is it a test only pin, or also it can be used for functional sacrificial path, and if it's a test pin, what does it do, right? Is it the clock, is it data, in, out, and so on?
Yeah. The other thing is, I love the idea of the ADK, MDK. Have OSATs or have other people signed up to follow it? Because I don't want to get a PDF and have to reconstruct all that myself. So if there's a fixed format that all of them follow, it helps my scripts and tools to read it. So how do we proceed in that direction?
Can I take this question? And you can help me out as well. So the format is just a format. The important thing is for ADK and MDK, actually ADK was contributed by Intel. And for both pieces, we have participation from the big EDA vendors. Now, creating a ADK or MDK, the authoring aspect of that is also important, and it's something that will be worked on. Probably not as part of the CDX, because that's not our charter, but you know, in general, in the industry, I expect that we're going to have tools that will be able to alter that information, check it, test it, make sure it's valid.
Okay, thank you.
Yeah, I want to add something to mention. I think we are collaborating with the JEDEC. I think so this will be part of the, I think JEP 30 is kind of an extension to this one. So same as like the CDXML that we've done in the past. So we work the Palo actively. So I think that will be actually another, I think, industrial standard, I think, targeting group as well. We also have other, I think, like the organization like SI2 that also participating in this. I think Mark is not here. I think he's one of them, I think, from SI2 participating. So we do have, I think, the more kind of getting, I think, across like the common industry, I think, standard organization, we all kind of agree. I think from different standard body, we need a kind of like standardized format, I think, for this.
Well, thank you.
Okay, I'm going to answer a question that nobody asked me.
Go for it.
I'm going to ask myself, so what about 3D blocks, right? What do we do about 3D blocks and where do we fit with that? Here's the good news. So 3D blocks is going to become IEEE standard. And we are in no way trying to compete with that. 3D blocks has specific application. And the 3DK that we're working on, the way we're looking at it is twofold. One is we will be compatible with 3D blocks, whatever shape it takes. And then second is really 3DK is a superset, right? We are defining materials and package routing rules and things like that, which are not necessarily in 3D blocks. And it's still a piece of data that you would need. And our collaboration with JEDEC is very important. So when you think about CDXML, you should also think JEP 30. We are working close with them, make sure we are fully compatible back and forth, so it's all the same thing. But thank you for the question.
Good question and good answer. Thank you, David and James. Thank you. We will break for lunch now. Thanks, everyone.
Thank you.